Hi, everybody, and welcome to this recorded Zoom interview with Ken Ridgway, geology professor, Purdue University in Indiana. Ken, what's the weather like? It's after sunset, isn't it? What's the weather like there in Purdue, at Purdue?
It's about 50 degrees. We had a little bit of snow a couple days
Oh,
ago.
wow.
And so, as we say back home, the hawk is coming out, and that's the cold weather. We know it's coming. The hawk
Oh,
is coming.
I love it. I love it. Well, thanks for sticking around so late on a work day. Viewers, can I talk directly to you for just a second? This is Ken Ridgway, and he is part of the Purdue team where we will be up in southern Alaska, or central Alaska, I guess. I don't even know where the hell I am with Alaska. I'm talking to a veteran here, but I'm going to be with Ken Ridgway, Michael Eddy, and Brandon Keogh next summer in June of 2026, and we're going to make a series of geology videos, part of the project, the Alaska project, that is already underway. So I've met Ken just once in the field on the Olympic Peninsula with Mike Eddy and Aaron Donaghy, and so here's a chance to visit again with Ken, and there'll be plenty more coming in the months ahead. Can you give us an opening statement, Ken? What are you hoping to do with us today, or just talk specifically to me? What are you hoping to share with me, and how might it help us next summer?
Well, I have a couple goals in mind. One is to give you a feel for the landscape that we're going to be on during the field trip
Nice.
so we can help coordinate that.
Good.
The other, for your viewers, is that we're going to be talking about the upper plate of Alaska, so the highest mountain ranges, big accretionary prisms, big faults. So this is kind of the iconic landscape that tourists see when they go up there.
Yeah.
And, the buses stop at some of the places that we're going to be talking about. So I think it'll give them a richer experience when they see this landscape. And this part of the Cordillera is a little bit different, and that's what I want them to see as well. But I think it has a lot of links with other parts of the Cordillera, but Alaska's always been kind of this oddball thing up in the Northwest, and I want to make some of those links as well.
That sounds great. I'm looking forward to this. Let's do a couple more verbal things before we go to your slides. I'm a rookie thinking about Alaska. You're not a rookie. When did you start going up to Alaska? How many field seasons are we talking about? And what are the main themes that you've been publishing on over the years?
So I've been going up to Alaska. I did my PhD there. My advisor was kind enough to let me go off on my own and do what I wanted to do. And so I started, my first field season was 1988.
Hmm,
And so I've been up there over 30 some years.
nice.
I missed two field seasons, like when my wife and I moved to Purdue, and then when we had our first child.
Yeah.
But otherwise, it has a strong pull for me, the geology up there, because everything is happening now. Or most of it's happening now, and there's earthquakes, so we can use geophysics. I like that, there's rocks to date, and I just feel like I'm in a landscape that, I haven't commandeered my way into. So, we have to get dropped off by helicopters
Yeah.
or canoeing.
Right.
And so I really like that aspect as well, that this is what, as pristine of a landscape as you can have basically in North America.
How were you trained? What was your PhD topic? And have you evolved over the years away from that original training?
Well, my PhD topic was on the Duke River Fault in the Yukon Territory.
Hmm.
And so I was looking at strike slip basins along
Mm-hmm.
it. As I moved over to Alaska, I would look over to Alaska and I'd see all this green on the map. And I would say, there's a lot of Cretaceous rocks over there.
Uh-huh.
And so I want to head over there. So I started doing a little recon over there. But I kind of fell in love with St. Elias during my PhD, and I've
Hmm.
always kind of gone back every few years and worked on some kind of problem in there.
Hmm.
Then I was working with a big group of people doing geophysics and geology
Hmm.
called the STEEP project, which was a continental dynamics project. And so that's when I really learned about the power of combining geophysics and geology.
Hmm.
And so I've kind of moved in that direction quite often. And then, occasionally I'll leave for a while and go work in Taiwan or go work in Argentina.
Right.
But I'm kind of like a salmon. I have to head back to Alaska every couple of years, and So it's hard to get that out of your blood.
I love it. How about one more before we go to the slides? I'm a big fan of Mike Eddy, obviously. So I've been collaborating with him with video projects and other projects down here in Washington and now up in Alaska for the first time for me. Mike showed up in your department. You must have had a hand in hiring him. What talents has Mike brought to the Purdue Geology department and maybe your work specifically?
Absolutely. Well, I've been recruiting Mike since he was about 12 because I knew he was a super smart guy.
Yeah.
And so every GSA meeting, I would try to catch up with him and always tell him about what we could do if we worked together at Purdue. And then when he started looking for jobs, I just pushed our department that we
Yes.
need to have a person that does this kind of geochronology.
Yes.
Because as you know, if we want to understand rates of processes and things, we need the tools that Mike has.
Mm-hmm.
And so, like on Aaron Donaghy's PhD project, these were rocks that I had worked on, the rocks on the Alaska side.
Yeah.
But going back in with Mike allowed us to really come up with very precise ages that we could tie into plate tectonics and tie in to Silesia. So he's been a game changer for me. And so, but I do want to say I recognized that when he was
Oh,
12.
there you go. When he was 12. And why not? Let's do one more. So the viewers not only know Mike Eddy very well, they know Erin Donaghy very well. We followed her from the start of her PhD at Purdue all the way through to the finish, and you were a co-advisor to the project. Can you comment? I know Erin's a superstar. Can you comment on your involvement with her and what you saw with her compared to, well, no, what's your perspective on what Erin did at West Lafayette, Indiana?
Well, again, and this time I'm serious.
Okay.
Erin, I knew as an undergrad. She was working with one of my previous PhD students, Jeff Trop at Bucknell.
Okay.
So I was in the field with her as an undergrad. She was working on a project we had in the Matanuska Valley, and her advisor at the time, Jeff. And so I realized that she had the ability to work hard, but she understood what the big questions were.
Yes.
And you can always, with students, as you know, you can have students that like the big questions, but don't want to do the hard grunt work.
Right.
And then you can have students that want to do the grunt work, but they don't want to see the big picture. And so Erin has both of those. And she has the ability to write. Sometimes she writes a lot. We call her the unabridged Erin. Sometimes Mike and I, but it's always high quality writing. And so I'm looking forward to her career. We have not just Erin, we have a number of young geoscientists in Alaska. You talked with Trevor before.
Yes.
Brandon Keogh.
Yes.
So I just love watching these students get ready to take off. It's going to be fun. And Erin's one of those that sky's the limit, basically.
It is. Well, it seems like you have an eye for talent. If you there's a lot of people that kind of pass by you, and you seem to be able to kind of put your eye and kind of point at a couple promising younger people. So it's working out for sure. Okay, well, I'll go wherever you want to go here, Ken. We're not going to go for an hour and a half. You got to get home and have some dinner. But let's see what you've got slides wise, and I'll just try to react to whatever you want to share. So if you want to, thank you very much. I can see your share screen. Look at that. There's the state of Alaska. Nice.
Okay.
Yes.
So we're going to be talking about the upper plate of Alaska, and I'll tell you why I differentiate it between the upper plate and the lower plate in a minute. But just for scale, here's Fairbanks, here's Alaska. It's about 400 kilometers as the crow flies. But what I want you to see, Nick, is that we have this very interesting shape where all the high topography of Alaska is right in this area, right in what some people would call the armpit of Alaska, because of this big bend here.
Yes.
And this landscape has mainly been developed, as I'll show you, the last 30 million years. And I'll show you some of the evidence for that. But for your audience, so Denali is right there. So the Alaska Range, the highest mountain range in North America. I want you to see the Foreark Basin. This is the Cook Inlet Basin here. This is at its widest point. It's about 145 kilometers wide. As you come up towards Anchorage, you can see the whole forearc gets uplifted and deformed. you could almost throw a rock across it, and it comes down here into the Chitina Valley.
Hmm.
So I want to talk about, why do forearcs get deformed like this?
Mm-hmm.
If you look out through here, this is the accretionary prism. So these are rocks that were off scraped. And you can see that they're not very well exposed here, but if you come through here, which is called the Chugach, this is the largest exposed accretionary prism on the planet, from what I've told.
Mm-hmm.
These mountains over here are called the St. Elias Mountains, the highest coastal range on Earth. These white peaks are the Wrangell volcanic field, which we'll see on the field trip.
Nice.
Some of the largest, both in height, they're up to almost 5,000 meters. But they're in a little odd configuration there, as you can see, this little belt in here. We'll talk about that. This is the Denali Fault, this topographic break through here. It comes all the way down through here to Kluane Lake.
Yeah.
There's a young fold and thrust belt out in here, which we'll talk about. So how did this landscape develop? And we think it's related to the collision of the Yakutat Terrane, which your audience has heard you talk about.
Yes.
So when you look at this map, it's the same map, but I've superimposed some other things on it. So here's the Yakutat Terrane or Yakutat microplate.
Mm-hmm.
So this is the lower plate that started out down by Silesia, where you're at today, Nick,
Sure.
and has been traveled along the margin, along the Queen Charlotte Fault, and is colliding now with this area. And we used to think that was the whole story.
Mm-hmm.
Now, with better geophysics, this outline here is from a velocity model from Eberhard Phillips based on earthquake data. We know that the Yakutat Terrane goes at least up to Denali. At Denali, it's about 150 kilometers beneath the upper plate. So what I want to talk about, and we can go anywhere that you want to go, but how does this upper plate reflect the collision and migration of the Yakutat? Because it makes all these like iconic landscapes that we think about when we see Alaska. On this map, we'll come back to it a few times, these triangles. So this is the Wrangell volcanic field. Here's the Aleutians here. Notice that there's a big gap in this magmatic belt here.
Yes.
And so that was one of the first things. And I started on this with Emily Finzel when she was doing her PhD here. She's continued to work on this at Iowa. So one of the first questions that we wanted to ask is, when do we get this magmatic gap? Because we know in other places where we have flat slab subduction, like in the Andes, in India, that the slab comes in at such a low angle that you don't have magmatism on the upper plate.
Mm-hmm.
So what we're going to look at is a transect from here to here, and Emily compiled all the ages of igneous rocks, plutonic and volcanic, here in that area. So this is from Emily's EPSL paper. Here's the Wrangels again, the active. Here's the Aleutians.
Okay.
This is the area where we have that slab imaged underneath the upper plate. So this is the Yakutat slab.
Yes.
And all these dots are the ages of igneous rocks along this transect. And you can see that at about 30 million, volcanism shuts off, magnetism shuts off. So that's an important number. I hope that your viewers take away, because 30 million is one of my favorite numbers up here. And I have several tattoos. No, I don't. But so I'll use this sketch to demonstrate some of the important concepts. So we know that magnetism shut off at about 30 million years in this area that I showed you with all the high topography. We want to know, well, when did this area start to get cooled and uplifted? And to do that, we use a tool called thermochronology. So I'm just going to show you some data from down in this area that we worked on with Ava Inkelman. So this is North America. This is the backstop that the terrain collided into, the Yakutat. We're just going to talk about her fission track data.
Okay.
And so what this says is that the Chugach terrain cooled from its peak was at about 20 to 40 I like to say the sweet spot is between 20 to 30 because, again, I like this 30 million year number.
Sure.
And so not only did magnetism shut off here, but these rocks on the Chugach side, as the Yakutat collided, started cooling between, 30 to 20 million years. And since we did this work, like Jeff Benowitz, Richard Leese, have even showed up here in Denali, these rocks cooled at about 22 million.
Mm.
So all this area of that high topography is cooling between 30 and 20, and the magnetism is shedding off. And so another question was, I'm going to go back one slide.
Mm-hmm.
I told you that the whole Four Basin's been uplifted. So for your audience, like in California, think of the whole San Joaquin Valley of Four being uplifted and squeezed close enough that you can almost throw a rock across it.
Mm-hmm.
So we wanted to know, when did the Four Basin shut off here?
Mm.
And the youngest rocks, you can see Emily there for a scale, we're doing field work out here, are these rocks called the Sadaka Formation. And these rocks are Oligocene based on the palynology. So again, that Four was being uplifted and deformed at about 30 million years. And we've done a lot of mapping, which I'm not going to go into detail,
Mm-hmm.
but that becomes important. So what I've tried to show you is that magnetism shuts off at 30. The rocks are cooling from 30 to 20 million throughout this area of the high topography, and the whole Four Basin, the Cook Inlet Basin, gets uplifted at that time, Nick.
Mm-hmm.
Now, there's some other cool things around this area of flat slab subduction. One is the Wrangles. As I told you, this is one of the world's largest volcanic fields. And so we've always used the age that Don Richter had. He was a USGS geologist that mapped these lavas, and his oldest age was 26 to 27 million.
Mm-hmm.
So again, that 30 window that I like. But Jeff Trop and other people have been out here working. There's a nice paper that they did. I think it's called the Geochronology of the Wrangell Arc. And the oldest lavas are 30.
Mm.
So again, it looks like this volcanic field started at 30 million as the slab is coming in, going underneath the upper plate, probably bringing in a lot of sediment with it.
Mm.
And that starts this big volcanic field. And this is, a strike slip margin, as you know, on this side.
Mm-hmm.
If we go up to that thrust belt and Foreland Basin that I mentioned to you, that's this area shown in TB here. We have 2 kilometers of sedimentary rock that are all mainly Miocene and Pliocene. But this thrust belt has been active, we think, as this flat slab has been inserted underneath of North America, underneath of Alaska.
Mm.
So we have shortening on the outer margin. We have subsidence. There's thick coal seams. This is where Fairbanks gets all their coal. So around that area, you can say that these things started in the Oligocene. When you think of the Oligocene, like 33 to 22 is a good number.
Okay, Ken,
So,
would you mind stopping your share? I'm hearing a theme here, obviously, around the number 30, and so my mind is starting to turn on what I know before 30 versus what all these developments since 30.
Sure.
Maybe we can just go back and forth like this, and then we'll go back to the slides. So if we go back in time, we're creating this oceanic plateau down in my neighborhood, Yakutat and Silesia together, starting 56 million years ago. We build the thing essentially in 5 million years or so. We can quibble a little bit, but that's fine. And I think Erin, I guess because of the work with you for her PhD, is not really docking a part of Yakutat down here. There's kind
That's
of
correct.
that kind of 2 forks of this thing coming away from the spreading ridge. Okay. I'm just wondering if you can help me get from 56 million years ago to 30.
Absolutely.
And that journey north, and plus, if there was volcanism in the Alaska Range area before 30, was there a subducting ocean plate up in front of that Yakutat plateau that's heading north as well.
Absolutely. So for the latter question, there's
Yeah.
definitely a subduction zone, and we have a volcanic arc system that
Okay.
during the Paleocene.
Uh-huh.
And so I'm going to use my hands if that's
Yeah,
okay.
sure.
So here's British Columbia,
Good.
the coast. Find the right angle there with
Yeah,
my camera.
good.
So Aaron showed that for the first part of Yakutat's journey, it was offshore and there was fine grained sediment and tuffs coming. And Mike
Good.
and her have been able to date those. We know it collided in the northern part, north central part of British Columbia.
Okay.
And we know that from the detrital zircons because we can tie those into the Coast Mountains batholith,
Mm.
which has very discrete intervals of magmatic flux events. So we can tie that in very closely.
Okay.
So it collided there,
About when?
and it collided there about 44 million.
Okay, thank you.
So it collided there, and then it was stuck for a while.
Huh.
And there's 3 kilometers of thick coal seams, weird rocks for the Pacific margin. It looks like the Mississippi Delta kind of deposit
Huh.
sitting there.
Okay.
Because you have this 30-kilometer thick piece of crust that doesn't want to go down, and it's just sitting there, and sediment's coming off the Coast Mountains batholith. And we think this is what shuts down the Coast Mountains batholith at 50, as you might know.
Mm-hmm.
So it's sitting there, and we have a transform fault, a paleo transform fault called the transition fault that's offshore of it. But then what happens at about 30 million, you know that was coming. Okay. And this was an idea that George Plafker proposed a long time ago, that the new transform steps inboard.
Mm.
And so now the Yakutat is exposed because it's going to get transported northward.
Got it. Got it.
And that transform is the Queen Charlotte, as you might know.
Right.
And so now this thick piece of crust has to get through the Yukon. And I think you talked with Trevor the other day, and he
Yeah.
talked about his orocline. That's a Paleocene event, about 50. So the way I look at it is that what Trevor's talking about with the orocline, it kind of put a bend in the road.
Uh-huh.
Okay.
Uh-huh.
But at 30 million, you had this dual semi tractor and trailer
Love
coming up, and
Love
it missed the curve. And it just went straight in to that curve. And that 30 million record is this record that we're seeing all over the upper plate in Alaska. And that's the ones that, again, people are going to see if they go down to the Kenai Peninsula and
Yeah.
see all this uplifted accretionary prism, or if they go to Denali,
Yes.
or if they go to Wrangell St. Elias.
Good.
That's the record of it.
Okay, this is fun. Okay, one more, and then we'll go back to the
Sure.
slides. I have been thinking a lot about Silesia for obvious reasons.
Mhm.
Aaron and Mike and plenty of others and
Right.
all of that down here in Washington. I've thought less about the Yakutat, but I'm comfortable with it based on what we've done with that story we just talked about. The Chugach, is that part of the northward? Like if we accrete Yakutat, we get it stuck, then we free it up, then we try to go around the curve. Is Chugach in that whole narrative you just said, or is that a totally different story from your point of view with Chugach?
No, so the Chugach, it got caught up in that collision. So we can see sediment coming off of rocks. Here we call it the Yakutat group,
Okay.
but it's part of the Chugach. So the Yakutat, when it hit British Columbia,
Yeah.
there was a long accretionary prism there
Okay.
because the Coast Mountains batholith is a huge magmatic belt.
Right.
So all of that sediment was there, and then it collides, everything gets stuck, but at 30 million, when that fault steps inboard, the Chugach and Yakutat have to head north. They don't have a choice in it because, as you know, the Pacific Plate's a big
Right.
plate. You're going to go, the car's leaving, you better go. It's like you're a kid going to school. And so they all had to go to school.
Does that mean the oldest part of Chugach is 44 million, or is there a much older
No.
story to Chugach?
The Chugach was forming above this subduction zone. The Coast Mountains batholith is over here. So you have a record from late Jurassic
Oh,
all the
oh,
way up to the late Cretaceous.
right. I
And
know.
even we've been able to show that it even goes into the Paleocene.
Are we deforming the Chugach a second time when we dock at 30 to the north? Or
Absolutely.
okay.
And we're even doing something a little meaner than that. In that we're also going to take a lot of it down the tubes.
I
And
see.
so if you look at the Chugach, it's nice and wide, and then it gets really thin,
Right.
like where the St. Elias is. And that's because it got caught in this collisional zone between this 30-kilometer thick crust
Right.
and North America, and it got pushed underneath. And some of that might be why the Wrangell volcanics are so big, because you
Oh.
have all this water saturated sediment,
Hmm.
and as you know, that lowers the melting point.
Yeah.
Put all that wet sediment underneath it,
Ah.
and it's still happening today. You have these big glaciers coming off, and they're getting sediment's getting subducted.
Nice. Hey, doing a great job. Thank you. This is a blast. Let's go back to the slides. And yeah, I mean, I'm getting more and more excited about the videos. I think we're just going to make a, I don't know, half a dozen short geology videos with Ken and Brandon and Mike and myself. And who knows, maybe we'll just kind of get some ideas about what we want to do video wise as we see some of these photos and get more of these concepts. This is like a little scouting trip here. I
Yeah.
love this. Yeah, great.
And this is what, like, as you mentioned on the field trip, you're going to fly into Anchorage this
Yes.
big day here,
Yeah.
and we're going to go and look at the uplifted Fort Arc Basin,
Okay.
look at the older parts of the Talkeetna Arc,
Hmm.
drive over to the Wrangles. If it's a clear day, that camera is going to be burning up if yours that video camera. 'Cause
Yeah.
these are, 16,000 feet volcanoes. People don't
Jeez.
realize how big they are.
Yes.
We'll ride up, look at the Denali Fault, look at Denali sitting over here,
Hmm.
this Foreland Basin, and then work our way back. So you're going to be really taking the tour of the flat slab topography
Mm-hmm.
that's related to it. Okay, so the last thing I wanted to mention before I go to the final two slides, Nick, is that
Yes.
over here in the Cook Inlet, there's about 10 kilometers of Cenozoic sediment.
Hmm.
And it's just a big clastic wedge, like this clastic wedge up here we're talking about with the Foreland.
Okay.
And what Emily and her students at Iowa have been able to show, we started thinking about it, but she's done a much more thorough job, is that as you started to uplift all this area or exhume it and cool it, then all that sediment started going out into the Cook Inlet.
Hmm.
And that's why you get this thick clastic wedge of sediment out here on the forearc off of the flat slab area. This is where all the gas comes from for Anchorage, you might know. And
Oh, wow.
people have looked for that clastic wedge further out in the Forearc Basin, but you don't see it there
Hmm.
because it's coming right off of this area of flat slab uplift where that plate is sitting underneath it.
Is it depositing right on Yakutat material?
It is down in here because
Hmm.
here this is the Yakutat exposed down here in the
Oh,
Santa Elias
right.
Mountains. You
Okay.
have big glaciers that are coming down and dumping that sediment on it.
I see. Yeah. Thank you.
So that's kind of the things I wanted to show you related to the field trip, Nick. But then I wanted to talk a little. I have two other slides.
Great. Great.
Actually, it's three other. But to give a kind of a broader context of what we're talking about here. So
Mhm.
here's the area that I showed you. Here's the lower plate. Here's the area impacted by the flat slab
Mm-hmm.
and all the features associated with it.
Mm-hmm.
But as I'm sure your viewers know, there was another period of flat slab, and this is, where are you at here? You're somewhere right in here, I believe.
Yes.
Out here a little bit more, right?
Yeah.
But this is the Laramide flat slab, and your viewers might know that we have this area where we have the Laramide uplifts, so like the Bighorns and the Beartooths and the Colorado Plateau, and all of this area going back to Bill Dickinson and Snyder back in the 70s and 80s is thought to be an area of flat slab subduction.
Mm-hmm.
And I think in Alaska, we have an example, an active example of
Mm.
what that looks like. This
Hmm.
Farallon slab is gone now. People have imaged it, but it's over in eastern US now.
Hmm.
But here we have it, the possibility of understanding what does the flat slab look like underneath of the upper plate.
Mm.
And that's what we've been working on recently.
Okay.
And so this image, so let me go back one for a second. So if you see Denali,
Yeah.
here's Denali here,
Yeah.
and this is going to be Denali right there. And
Okay.
this is a tomographic image, and this is after the Earth scope data.
Hmm.
So we have all this rich data set that we never had before.
Mm.
So what I want you, this is a three-dimensional object that we're looking at here. So here's the coastline. You can see the flat slab coming in, and it's right underneath of Denali there, where
Hmm.
my pointer is.
Hmm.
And that's all we could see before. And that was based off earthquake data. We could image that. But what's been really exciting about the Earthscope data, and we've always had this ongoing lively debate with the geophysicists,
Hmm.
and we would say, hey, we're seeing this record of 30 million on the upper plate. And they would say, well, Ken, if I take this point here that I can see the slab, the Yakutat slab, and I use modern day plate subduction rates, this point would be back at the collisional zone at 10 million years.
Hmm.
So they would say, we've only had flat slab subduction the last 10 million years.
Okay.
But again, it didn't fit with the geologic record. So now what we're seeing, and this is the work of Gary Pavlis and other people,
Hmm.
and that area there goes into this flat slab that's going directly south, Nick,
Mm.
directly into the mantle, and that's what this area is here. And it's got here's the 410. So this is the start of the transition zone in the mantle.
Okay.
So this slab is doing a U-turn and it's anchoring down into the mantle. And there's this new idea out there in orogenic systems that when these slabs get anchored into the lower mantle is when you start to have crustal thickening and start making mountain belts.
Mm.
So what we think is important here is that Gary's done some calculations. If I take all this back up, then we would have started subduction at about 30
At
million. So
about
now the
30.
geophysical data
Mm.
fits with the surface geology data. So this is what we're writing up right now. It gets even crazier as you move down into the mantle. This is a part of the slab itself. It almost turns southward, as you can see.
Mm.
And we think what happens is that this was a much broader convergent margin. And what's going on is that the subduction zone is actually overriding itself, if that makes sense. So if you look at my
Hmm.
hands, here's the original slab. And you were asking about that. What do we have before 30 million? There's the subduction zone there.
Right.
But what happens as Yakutat comes in, this thing starts to turn. It becomes like we call it a recumbent fold.
Hmm.
It turns back into where the old subduction zone was.
Mm. Mm.
So this is that bulldozer that I was talking. This is the twin tractor and trailers that
Yeah.
collided into the margin. So this is something that we're trying to write up now, but we would never have had this image without the Earthscope program to be able to see deep into the mantle. And I know you've had some other speakers in the past talk about some of these slab images as they go into the mantle.
Hmm.
So I wanted folks to see that, to know that these are the kind of problems that we're working on in Alaska, trying to combine geophysics and what we're seeing at the surface.
Well,
But
that's the fun part that late in your career, I mean, we're the same vintage, Ken, and I don't know, I'm guessing I'm going to add some narrative without really knowing what I'm talking about. Maybe for 20 years you kept saying, "Okay, I'm starting to hear about this mantle tomography, but we're 20 million years off between what I've got at the surface and what you guys or what we have as far as peeking a little bit into the subsurface." And now, late in your career, you can make up for that lost missing time of 20 million years. That's the disconnect. That's the promising hope, I think, eventually for us to match surface geology with mantle tomography. Is that narrative kind of what you've experienced in the last 20 years?
Absolutely.
Okay.
These high resolution geophysical models are changing the way that we can interpret the surface geology and
Mm.
making sense.
Mm-hmm.
Where before, if we just ran a seismic experiment and just looked at the upper crust,
Yes.
it still leaves too many holes for us, Nick.
Right.
But if
Right.
I can look and say the whole Yakutat slab turns and heads down to the mantle,
Right.
and then it gets kind of, once you hit the lower mantle, it gets anchored.
Yeah.
And so then we can start to understand why we have all those high mountains in
Mm-hmm.
Alaska,
Mm-hmm.
why we have, big volcanic fields as it relates to the flat slab coming in. So
Mm.
I think that's a really beautiful story that Terry Pavlis, Gary Pavlis, and a lot of other co-authors and I are writing up right now. So I wanted your viewers to see that. And then my last slide
Yes.
is I just love this seismicity map. And so because it tells so many beautiful stories, Nick, about what
Uh-huh.
we've been talking about this afternoon.
Right.
So here's the seismicity. I had this made like in 2017 from the Alaska Earthquake Center. So the important things here is that blue or shallow earthquakes. So you see all the blue here.
Mm-hmm.
Red or deep earthquakes. You can see those in here. So out here in the Aleutians, you have a steep subduction zone. The slab is going down steeply. So all the blue is right at the subduction interface. And by the time you get on the other side of the Aleutians, you have a steep slab.
Mm.
But look what happens in the area that we've been talking about, buddy.
Mm-hmm.
You come up into this armpit where the Yakutat's colliding,
Yes.
things get crazy. So here's the Queen Charlotte.
Huh.
We talked about the Yakutat coming down through here.
Yeah.
It's this block sitting in here. And what's amazing about it, but also what makes me think it's equivalent to what we're talking about with the Laramide flat
Mm-hmm.
slab, is way out here in the McKenzie Mountains. So 1,500 kilometers away, the folks that are working on the seismicity here feel like it's related to the collision of the Yakutat. Look how far the shallow earthquakes, they go all the way up to the northern Brooks Range.
Whoa.
And so you see this kind of deformation like in the Himalayas, where you have these big collisional zones and you have all this deformation distributed
Mm.
across the upper plate.
Mm-hmm.
Something that the geophysicists at University of Texas are working on is this band of seismicity out in here.
Mm.
And what they're thinking is that as the Yakutat is getting pushed underneath the continental margin, you're actually starting to tear the Pacific plate right there.
Mm.
And so this is such a dynamic picture
It is.
of
Yes.
what you're going to be seeing on the field trip and
Nice.
how things are represented at the surface. And there's really very few places like this besides like the Himalayas or the Altiplano region down in the Andes, where you have, again, flat slab subduction going on. Flat slabs, flat slab subduction just builds high topographies. I mean, India is kind of the ultimate example, the India-Asia collision
Mm-hmm.
of flat slab subduction.
Mm.
So you have the Himalayas, you think of the high parts of the Andes, it's the Altiplano region. You think of North America, it's Alaska. So I think that's a pretty cool theme to think about when you're thinking about Alaska.
I love it. I love it. And if you got a glass of water there, help yourself. If we can stop your share, we'll just add a
Yep.
little tack, couple things on at the end, and I think we're good. Beautiful job today. You're a natural. Weird shoehorn of something in right at the end, but the project that we're part of is 200 million years older, right? I mean, we're way, way back in geologic time.
Absolutely.
Can you give us just, it's not the topic of today's visit, but subduction initiation involving the talkite and the arc. can you just remind everyone, including me, does that topic have anything to do with what we talked about today? Are we going to making videos on the Talkeetna Arc? What kind of connection at all can we make between the project we're going to work on next summer and this topic today?
That's a good question. So the Talkeetna Arc really is the starting point for subduction initiation in Alaska modern coordinates. We'll talk about where Alaska
Right,
was. Keep
right,
that in mind, buddy.
right, right.
Um, as you know from some of Brandon's work, the PhD student that's working with Mike and I, we think all of that is related down to the Bonanza Arc down in Vancouver Island. So basically, you start this subduction zone in the Triassic,
Okay,
and things are getting rifted off of the margin, is what our working hypothesis is.
okay,
You form either by having a hot spot, like you form an oceanic plateau, or you just rift it enough that you attenuate the crust enough, you start having things like the Nikolai flood basalts. And so you start flooding all of that area. So what we're doing here is we're making a convergent margin, and we
mm-hmm.
spread all this material out. There's complex subduction zones like the south, western part of the Pacific, and then we're going to accrete it all back onto the margin, basically. Some of it stayed there, we think.
Yeah.
Some of it didn't. And I think, as you know, there's been a long-term problem with Baja, BC. That's one of the big outstanding controversies. I think you did a topic on that. But people have argued for, 30 years, like, well, my piece didn't move.
Right.
Someone says my piece did move.
Right.
Well, I think what Brandon is showing is that if you rift off that, you can leave pieces on, but you also have no extension is pure extension. There's always an oblique component.
Mm-hmm.
And so you can move things along the margin with this oblique opening. And what we're going to see when we're in Alaska is that when you had this, what we're inferring as extension, you had ocean basins, small ocean basins in between. And we call, in our area, we call them the Kahiltna. They're called the Gravina down in British Columbia.
Yeah.
And then when we shet everything, some of that gets pushed underneath of the margin, underneath of active arc systems, and you form things like the McLaren schist. You might have heard Trevor talk about that. I think it's related to like the Rand schist down in California. There's a big event.
Yeah.
There's a number of big what word am I? Bandit Nices in your area.
Yes. Yes.
I think all of those based on what Stacia Gordon and her students are working for. So that's the shedding of this big extended area. So think of the Mediterranean like Greece and all the islands. And then if you close everything together, and to make it even more complicated, you got to throw in big strike slip faults, which we have to talk about.
Yeah,
but we're going to have fun figuring that out.
Yes, and I'm going to be trying to think real hard between now and next summer about the chronology of this. It feels, at least as a rookie, it feels like there's these rhythms to this performance, and then the performance starts again. A little bit younger. We just keep doing the same thing. We're accreting stuff, we're slicing it, we're sending some of it north. And so that's kind of a fun through line. And I'm just starting to think about some of that. Ken Ridgway, would you please hold the line? I'm going to stop the recording. We'll chat a couple more minutes before it's time to go home. But thank you so much, thank you so much for your time today. You did a beautiful job. Thank you, Ken.
I enjoyed it. Thanks for the opportunity.
My pleasure.